Okay, so today we're going to talk a little bit about core analysis. We're going to review some concepts and talk a little bit about Wellog's interpretation and a little bit of petrophysics. So I'm going to be all over the place. The idea here is to review some concepts, and so I'm gonna try to be more consistent with making videos and things like that in the near future. Okay, so first we're gonna review what core analysis is. You know, it's a very important thing in the oil and gas industry. Let's go with the AI version and what Google says. Okay, but core analysis, English, please. So, core analysis is the laboratory study of rock samples, cores, extracted from geological formations during drilling. And it provides ground truth for understanding a reservoir's physical properties, reducing uncertainty in oil and gas exploration and carbon storage projects. So why are we talking about ground truth? Because usually the measurements that we get from well logs are indirect measurements. So sometimes we measure resistivity, gamma ray radiation, other types of radiations, nuclear bombardment particles, and from these signals we try to get indirectly to the petrophysical properties of the rocks. So that has a certain grade of uncertainty included, right? And on top of that, well logs can be affected by different things: temperature, pressure, the shape of the well bore, like the wall of the well can. Also, the fluids that are being used for during drilling can affect the measurements, because pretty much what we are doing is reading resistivities. We are bombarding or hitting this matter with certain grades of radiation, and we or let's say the sonic wells, which send a acoustic signal, you know, and then we hear back the echo and stuff. These things can be affected by the medium, right? But if you have a physical core that you can test on a lab, of course it's going to be ground truth. So once we have the cores or the rock samples from the extracted, we can run some analysis. One type of analysis that is very common is routine core analysis, RCA. So what do people do with RCA? RCA, as we can read here, focuses on basic physical properties, usually performed on plugs. What is a plug? A plug is a small cylindrical sample. Let me show you here. Plug. A core plug. Good. So this is the actually this is how they take a core, but actually the plug is not this. The plug is taken from the core like this. So this is, here we have a core sample, and from this core sample we are extracting a cylindrical small sample, which we call core plugs. Okay, so in these small cylindrical samples we can test things under standard laboratory conditions. When it comes to laboratory conditions, we have to understand that the rock is buried inside the earth, right? And down there the rock has certain conditions of temperature and pressure. When we take the core out to the surface, we are changing obviously the we are changing the environment, the conditions. So the laboratory conditions are different from the real reservoir conditions, right? And sometimes people make corrections. Sometimes people try to simulate the reservoir conditions so that they can test and measure these properties under reservoir conditions. Okay, this is something important that we have to mention here. Okay, so another thing. So what is usually measured in RCA? RCA measures porosity, okay, permeability, fluid saturation, and grain density. Okay. Sorry, I'm clearing my throat because I'm losing my voice right now. So I don't know why. I need something to drink. So porosity. So what is porosity? Porosity is measuring the void space within the rock to determine how much fluid, oil, gas, or water we can have. Okay. The permeability, it is assessing how easily fluids flow through the interconnected pores. Okay, so some important thing here that we have to mention is that porosity is usually measured using let's say a permeameter. Let's call it like core lab permeability measurement. Let's say, for example, the CMS 300 is pretty common use. So with the CMS 300 core measurement system, we can determine like porosity up to 40%. We can determine permeability, air permeability, equivalent air permeability at a specific mean pressure. And we also can calculate the Klinkenberg permeability. And this is like something important to mention here. But first, let's clarify how porosity is measured in RCA core analysis. Okay, so during RCA, porosity is measured by determining the ratio of pore volume VP to bulk volume VB of clean dry core samples of blood. So primary methods include helium expansion. So this is why sometimes they use helium or other gases because they use the Boyle's law. Okay, I don't know how to pronounce this word, Boyle's law. I'm gonna say Boyle's law, but I'm not sure. But so the helium porosimeter, Boyle's law, is considered the most accurate. And how does it work, this method? So the method uses helium, which penetrates small pores. Okay, so the system is injecting the helium and is going to determine the grain volume through the gas expansion. So here we're going to be using ChatGPT to help us understand how porosity is calculated from Boyle's law in RCA. So here we have an example of it. So for this example, what we have is we have a volume of block, which we're going to call, let's say, BV, which is 65 cubic centimeters. Then we have a reference volume of 100 cubic centimeters. That is the volume of reference. Then we have a empty sample chamber volume, which we are going to call V cell, which is 120 centimeters cubic. Then we have initial reference pressure, initial chamber pressure, and final equilibrium pressure. And the goal that we have is to calculate grain volume, pore volume, and porosity. So yeah, in routine core analysis, a clean and dry core plug is tested with the helium porosity. This is actually important because you have to clean and take all the fluids out, and maybe later in another video we're gonna focus or talk about the cleaning process of plugs. They use usually the technique that they use the most is Dean and Stark method. So maybe we're gonna be talking about this one in the next video. So the Boyle's law concept in helium porosimetry, helium expands from a reference chamber into the sample chamber. Because helium enters the connected pore space, the volume excluded to helium is mainly the grain volume. This is the volume that it is in the way. So the accessible chamber volume is the volume that is accessible. It is the volume of the cell minus the grain volume, because the grains are occupying a space where helium cannot enter. So how can we calculate this grain volume that is in the way? Okay, so this grain volume is going to be calculated using the Boyle's law concept. So as you can see here, when you open the valve and you let the system get into equilibrium, you have a initial phase and a final equilibrium phase. So your initial conditions are going to be P1 V1, and then end conditions are going to be P2 V2. Okay, we already said that the accessible volume is going to be the V cell minus the volume of the grains. So if we can get V grain, the volume of grains, by like clearing this equation. So we put this one on the left, so the volume is going to be V cell minus the accessible volume, right? But so we already have V cell. We have V cell, but we need to calculate the accessible volume so that we can find this one, right? So how can we calculate the accessible volume? So the accessible volume is gonna be, this calculation comes from a gas balance using Boyle's law. So in the porosimeter, helium starts in the reference chamber at high pressure and expands into the sample chamber. Okay, so we start in the reference and we go through the sample chamber. Okay, the sample chamber is not empty. It is initially at atmospheric pressure. So this is the equation that you have. So P1, which is the initial pressure in the reference with the volume of the reference, plus the initial pressure in the sample chamber with the accessible volume for helium, which is accessible because we are considering the sample which is taking space, and that is going to be equal to the final equilibrium pressure of the system and the two volumes, the reference volume and the accessible volume. So if we want to get the accessible volume from this equation, we have to move terms around, factor both sides, and so the equation that we're going to get is that the final equations we're going to get is the accessible volume is going to be the reference volume times the initial pressure minus final pressure the initial pressure in the reference chamber minus the final equilibrium pressure, and then we divide all of that by the final equilibrium pressure minus the initial pressure in the sample chamber. So we plug in the values and we get the accessible volume. Okay, and once we have the accessible volume, well, we already know from this equation that the volume of the grain volume is going to be V cell minus this accessible volume. So So V cell, we already knew that it was 120, and with the calculated accessible volume, then you get the volume of the grains, the grain volume, which is 51.99 cubic centimeters. And now with this 51 grain volume, you can calculate the pore volume now. So pore volume is going to be the VV volume of the sample. We already know that the bulk volume of the plug is 65. So 65 minus the volume of the grains is going to be that you calculated before, right? We get the pore volume of the sample, and to translate pore volume into porosity, you have to divide this pore volume into the volume of the sample. So it's going to be 13 divided by 65, which is our original volume of the plug, and that's going to get us 0.2, which is equal. This is fraction, but in percentage, is going to be 20%. Okay, so this is how the system and this is how the porosimeter is working, and how it is calculating the porosity of the sample. Okay, so later in another video we're going to cover how the permeability is measured, and the differences between air permeability, concave permeability, things like that. But we're gonna call it a day for today, and thank you guys for listening to these oil and gas, petrophysics, core analysis kind of like topics. See you in the next one.